Hello, welcome to my advanced computer programming project on IoT traffic anomaly detection system. This project addresses a critical security challenge in modern smart homes and IoT networks. Let me start by explaining the dataset. I worked with 10,000 network traffic records and collected from various IoT devices, including smart thermostat, smart lock, cameras, locks, and sensors. And the dataset contains 12 original filters, temporal information, and network identifiers, protocol information, and traffic metric size. And most importantly, labels indicating normal or attack traffic. I began by analyzing the data quality and distribution. I created 10 different visualizations, including correlation, heat map, or others. So in here, I have first 5 records of dataset, and there is a missing values in flag column. You can see around 2000 missing values, and all these saved to in figures directory. The dataset is perfectly balanced, almost perfectly balanced with 50-50 percentage and normal and anomaly traffic. This is my system overview. We are collecting anomaly data, processing and cleaning it. After that, analyzing 5 parameters, then creating 4 machine models. XGBoost, random forest, SVM, logistic regression. We are training models on 8,000 anomaly data and selecting best model, and if success, converting model to API. This is where the magic happens. I engineer new features. First, I load a dataset. After that, time-based features extracted from timestamp. There is a port categories. If bigger or greater than different numbers, it well-known registers or dynamic or private. We have payload ratio. It calculates how much of the package is actual data versus overhead, and I remove the unusable columns like timestamp, IP addresses because they are unique, and fixing missing value that are maintained here in flags. I fill in with them none. I standardized 11 numerical filters using standard scaler in here. Is ensuring all filters contribute equally to the model. This is crucial for algorithms like SVM and logistic regression. I split the data with 80% for training, and I use stratification to maintain the class balance in both sets. This modular approach made debugging easier and allowed me to optimize each step independently. For the machine learning phase, I trained and compared 4 different algorithms: random forest, an assembly of 200 decision trees, XGBoost, gradient boosting with 300 trees, supporting support vector machine with radius basis function kernel, logistic regression as a baseline linear model. After after training all model on 8,000 training samples, I evaluate them on the held out test set of 200 samples, as you can see here. And according to this result, XGBoost achieved 47.84 F1 score, which is the best performance between these models. You might notice these scores are lower than typical benchmark, like 80% or 90%. And this is actually revealing important characteristic about our dataset, IoT dataset. The relatively balanced uh, performance across models, with Xjibus leading by about 1.3 percent point, suggests the dataset has complex and overlapping patterns between normal and attack traffic. Looking at the confusion magic Xjibus in here on the set of 2,000 samples. Upper left are true negatives, which is normal traffic correctly identified as a normal, and in here lower right true positives, 453 attacks correctly detected. And important, IoT network traffic anomaly detection is a challenging problem. The overlap between normal and anomalous behavior in IoT devices is significant. However, XGBoost still outperforms all the other models, and this is the best we can achieve with this particular dataset and feature set. In real-world deployment, this will be combined with the other security layers. Despite the moderate scores, I selected uh, XGBoost as it consistently performs the best across the all metrics. Then I retrained it on the entire dataset of 10,000 for production deployment. This gives the model maximum learning capacity and should improve its real-world performance, as you can see here. Now for the API implementation, I built a production-ready RESTful API using Face API. Now, let me show you how the API automatically load all the trainer artifacts on startup. This is one of the key features of the production system. So I use Face API startup event decorator. This function runs automatically when the service starts, so no manual configuration needed. The system loads six critical artifacts. Model is the trained XG boost classifier, scalar for normalizing numerical features, dic encoders, dictionary of four label encoders for categorical features, feature columns, ensure filters are in the exact same order as training numerical features, list of which features need scaling, production metadata, model performance information. Now let me start the server to show in this action. Green check mark confirms each one artifact was successfully loaded. The entire loading process takes less than a second. Let's open the server. Uh, let's start with model info. Try that, execute. As you can see, the metadata is immediately available through the API. Here you can see model name, F1 score, and training samples. When a prediction is made, all the artifacts work together. encoder transform categorical data, filter columns and choose columns order, and scalar normalize the numbers, model makes the prediction. All of this happen in 1 millisecond because everything is already in the memory. As you can see, machine says this is an attack. Confidence ratio is 0.52. Let's try another one. Now it said normal and confidence is 0.60. Now this is my front-end IoT traffic analysis dashboard. Third model type is JBush. Accuracy is 0.47 and 10,000 training samples. Back algorithm is XGBoost. Let's make a prediction. Prediction result is attack confidence is 57%. Field I put the field random data for numerical data. As you can see, still attack but confidence is shrinking. So thank you for listening.